first 45 minutes of a lesson and then give you the rest of the time trying to split it up. This topic's quite hard to do that though. So I'm going to give you the rest now, and I might hold an example over until Friday. So first of all, here's some notation. We touched on this notation, we didn't quite get there. And it's on the OneNote, so you don't necessarily have to write it down. If you're writing down examples, you'll see this notation a little bit later. But I'm going to talk through it, and I will give anybody who wants to write it down and start right now, I'll give you enough time to do that if you'd like. So I'm going to talk through it very quickly. This notation is based on the question we just did earlier. We want to find, we want h equals 0, but we can't divide by 0. We also cannot find the gradient of a single point, as we've discussed. Here's our function. It's the function we had earlier. So for the example, mathematically we would say that the gradient is equal to the limit as h goes to 0. So we talked about limits end of last week, I think. And then we would do our y2 minus y1 over x2 minus x1. And I introduced this notation to you earlier as well. So our y2 coordinate is the x plus h. It's the x plus a little bit, which in this case is 3 plus a little bit. And f of 3 plus h, or x plus h, is the y value. So that's y2, that's x2, that's y1, that's x1. And we go through, that's just our gradient formula. It looks really complex, but it's just the gradient formula we used in year 8 and 9. Then the limit of this, I substitute those values in. And we did this last question, okay? We just didn't have that limit as h goes to 0 on there. The limit as h goes to 0 of this, I've just expanded the brackets. I've cancelled out some common numbers, this time without any mistakes. The 18 and the 18 cancel out, the 21 and the 21 cancel out. I might have put them together and made 39 before I cancelled out, doesn't really matter. Either way, they're gone. 12h and 7h combined to make my 19h. 2h squared is 2h squared. And then I divide by h through. Each individual term has to be divided by h. If you're getting this wrong at any point, and I'll show you an example of this in a minute, can I strongly urge you to factorise the numerator and then cancel the h out. Each term has to be divided by h. It's a really common mistake for people to look at this and go, oh, 19h divided by h, the h's cancel out, and leave that as 2h squared, which would be wrong. Actually give you the same answer in this question, you'd be lucky, but it would be incorrect. Then we go down to here, we go, the limit as h goes to 0 of 19 plus 2h. We were verbalising this solution a minute ago. We were just saying, well, clearly that just goes to 19 as h gets really, really small. But now we're going to do it mathematically, where we say, even though we can't divide by h up here, mathematically the limit, so we're not saying h equals 0, but the limit as h goes to 0 is, as h goes to 0, the limit for h is 0, therefore the limit for this will be what we get when h is 0. So we put h equals 0 under there, we get 19. So that's building up that process. Now we substituted 3 in at this point. So this gives us the gradient at x equals 3, but only at x equals 3. We are going to build up the gradient function otherwise in a second, so the generalised gradient function in a moment. Is anybody writing this down? Cool, let's roll on then. So example 2, this is your question 3 from 18A. Let's go through it, and I'm going to do part B by factorising the top. Yeah. Question B doesn't work so well. I don't know why I've got question B there actually. I made this a little while ago, we'll question mark that. Question A though, the limit as h goes to 0 of that function, what happens as h goes to 0 there? We're left with 5, good. So basically the limit as h goes to 0, we investigate what happens when h equals 0. We'll talk about B in a second. C's an interesting one, it does come up. What's the limit as h goes to 0 of 7? 7. And this is a really simple question that can fool some people because they overcomplicate it in their minds. There's no h's there, there's nothing to let equal 0. The limit as h goes to 0 of 7 is just 7. And question B, we can investigate that, although it's a little bit beyond what we need to do. What we can't do in this case is cancel out the h, because some of the terms in the numerator don't have an h in them. So we could investigate this by looking at, well, what happens as h is equal to 0.01. or 0.001 and investigate what happens. I suspect what will happen is that this term here and this term here will progressively get tiny and then disappear. But these two terms here will end up being divided by the h, which is really, really small, which means these two terms get really, really massive. So this, I suspect, is heading towards infinity because of that, the massive nature of those two terms. Irrespective of what x is, that -7, in fact, is probably heading towards negative infinity, because that -7 divided by h, where h is really small, is going to be massive, and everything else won't matter. So we've got that, although I'm not sure if I meant to add that question there. You might find question 3a, I chose these while being guided with the textbook, and I've left mine over there, has question 3 in 18a has some of these questions in that ask you to investigate around that. You won't get that in a differentiation by first principles type question, but it explains the exploring around x equals 0 concept. Let's do a generalisation now. So we've talked about how to find by first principles the gradient at a point. Now we're going to find by first principles the gradient function, so that we have some sort of function that will give us the gradient at any point, at any time that we want it. We can just substitute into that function. So I'm going to build that understanding. I'm going to do one of these gradients, and then I'm going to dole out the rest to you guys to do, and we're going to build this table and investigate what the gradient function looks like. So which one would you like me to do? 0, 1, 2, 3, 4, or 5? 5. I'll do 5. So I want to find a gradient at x equals 5. So my gradient will be equal to the limit as h goes to 0 of, there's my function there by the way, but of this, f of x plus h minus f of x over x plus h minus x. Do you see that the first line of my working is the same every time. I'm finding the gradient at a point this time though, so I know what x is. X is 5. My denominator cancels out nicely again, as always, as h goes to 0, of f of 5 plus h minus f of 5 over h, and then I substitute in my numerator. So the limit as h goes to 0, I'm going to just scoot across and make this a bit bigger, as h goes to 0 of 5 plus h, what's the function again? 3x squared plus x minus 6. So this is 3, 5 plus h squared plus 5 plus h minus 6. And then that's minus f of 5, which is 3, 5 squared plus 5 plus, what is it? That's x, plus 5, and then minus 6. All over h. And now I'm going to simplify my numerator. H goes to 0 of 3 times 5 squared is 25 plus 10h plus h squared plus 5 plus h minus 6. 3 times 5 squared is 75, so minus 75 minus 5 plus 6 all over h. This is equal to the limit as h goes to 0. I expand that bracket now, I get 75 plus 30h plus 3h squared. That 5 cancels with that 5. That 6 cancels with that 6. I'm left with just negative 75 and a plus h all over h. The 75s cancel out, which leaves me with the limit as h goes to 0. That's pretty poorly written. Of 31h plus 3h squared over h. But I'm going to show you this factorisation skill now. I'll just do it one time. And if you're getting this, because we have to divide everything by h now, if you're getting that wrong or if it's difficult for you, use this factorisation technique. So what you can do is the limit as h goes to 0 of h times 31 plus 3h. I've just factorised the numerator. I've factorised the value on the denominator out of the numerator, because then I get over h and I can just cancel those, because I now have just one term on top, effectively, which gives me the limit as h goes to 0 of 31 plus 3h, which just equals 31. So my gradient at x equals 5, I'm zooming out there, is 31. You guys are going to tell me the gradient at x equals 1. You're going to tell me the gradient at x equals 2. You're going to tell me the gradient at x equals 3, x equals 4. Got it? Go. Okay, so in the gap between recording, we have determined each of those point gradients at 0, 1, 2, 3, 4, 5. And we've spotted a pattern in that they're going up by 6s, and then we created that linear function because it was clearly a linear function. The gradient equals 6x plus 1. I don't want anybody to make the assumption now that gradient functions are always linear. They are sometimes linear under special conditions. We'll get there, you'll see. And by mid next week, this whole process will be a lot easier. So let's carry on just quickly. We did that. I had this set up, but you've already done it, so I don't have to worry too much about that. But at 0 we get 1, and then we get 7, and then we get 13, 19, 25, 31, and it gave us that really nice linear pattern, which was that the gradient was equal to 6x plus 1. So that was nice, and that actually works for any point. So we've got a gradient function now for that quadratic. If I want to know the gradient at 10, I'd do 6 times 10 plus 1, 61. If I want to know the gradient at 1,000,000, I'd do the same process. So we've got a gradient function. Now we don't have to do first principles every single time we want to find a different gradient. So that's really good. Let's look at the generalisation in terms of first principles. And then I've got example 3, and then I'm going to be almost finished. I'm going to leave example 4 for Friday. So the first principles generalisation is like this. In fact, I'm going to take this. No, I'm not. That'll make it too confusing. Forget that. First principles generalisation is I want to find a gradient between 2 points. My 2 points are x and f of x. And my second point is x plus h and f of x plus h. But I'm not using 3 this time, I'm using x. So I'm keeping it general. And then we'll be able to find the gradient function for x, not for 3. So we'll go from there. Notice here that this is x and 3x squared plus x minus, what was the subtract? 1, 7, 6. 6. I don't know where I got 1 or 7 from. Minus 6. And this one is x, comma, 3x plus h squared plus x plus h minus 6. We did all this simplifying earlier. And the gradient, m, is equal to the limit as h goes to 0 of what do we got? F of x plus h minus f of x over x plus h minus x. And I'll zoom in on this now. It's the limit as h goes to 0. Stop me if you need me to stop, but I'm going to be reasonably quick on it. X plus h squared plus x plus h minus 6. That's my f of x plus h. Minus f of x, which is just, so that should have a 3 in front. 3x squared plus x minus 6 all over h. That's equal to the limit as h goes to 0 of, and I'm going to expand this in one go. I get 3x squared, and then I get plus 6xh, and then I get plus 3h squared, and then I get plus x, and then I get plus h, minus 6, minus 3x squared, minus plus x, and then minus 6, that should have a bracket around it there, my apologies. This is the problem with speed. So that actually will be negative because we'll have minus positive x, and this will be positive because we'll have minus negative 6. And with an orange pen now, 3x squared cancels with negative 3x squared, x cancels with negative x, negative 6 cancels with positive 6, and I'm left with the limit as h goes to 0 of 6xh plus 3h squared plus h over h. When I cancel an h out of each of those terms, I'm left with the limit as h goes to 0 of 6x plus 3h plus 1. And if I let h equal 0, to simplify this, I get 6x plus 1, which is exactly what we got by building that pattern earlier. So the gradient function, we were doing point gradients earlier. The gradient function for the function 3x squared plus x minus 6 is 6x plus 1. And I promise you, next week there is a really nice pattern that we'll build from this, but for now that's the gradient function. I just want to do example 3, talk to you quickly about notation, and then I'm done. And I know it's 10 past 10. We're going to determine the derivative. So I've introduced a new piece of language already. The derivative is another name for the gradient function. Determine the derivative of y equals negative x squared plus 6x by first principles. Would you like to have a go at this yourself, or do you want me to just do this one and then give you the exercise to practice? I've got give us a go. I've got pointing fingers at me. Okay, give us a go is the only vote I've got. So I'm going to pause. No, I'm going to do it anyway. So, okay, so here's the question I just left you with. I know I gave you 4 to 5 minutes, which is probably not quite long enough, particularly early on in your learning journey. But here's my solution, so we can just move on, and you'll get plenty of time to practice this. I'll just run through this quickly. I might do it on here for the benefits of anybody who's watching the video as well. So in the first line, this first line here is standard fare. But can I just make this note now while I've got the opportunity to? That x plus h minus x always ends up being h, but I would still always like you to write that first line. I'd still like you to make the note that it's x plus h minus x in one line, then simplify to h. It's a really important piece of working that shows you're using the gradient formula. That's the first bit. The second bit is I've used that function. F of x plus h becomes negative x plus h squared plus 6x plus h. And then I've got minus. The second bit, because I'm subtracting it, I always put that in brackets so that when I do negative of a negative, I don't get that wrong. And in particular, when I do negative of the second term, I don't get that wrong. So you should always put that second one in brackets at least. And I end up with h in the bottom. In the third line, I've expanded brackets, the x plus h squared in particular, and done some simplifying. In the fourth line, I've continued to do that simplifying by expanding a second set of brackets. I am going to pretty much overwork every one of my examples, and I'm happy for this to be, if you're not quite sure, do this level of working. Some of you, though, will be looking at these two lines going, I could have done that in one line and got it right. That's perfectly fine. But I'm going to go to the lowest common denominator in each of my sets of working. I get down to here. And then when I divide everything through by h, you notice I haven't factorised here, but you could factorise the numerator if you're worried about getting it wrong. I divide everything through by h, I end up with negative, limit as h goes to 0 of negative 2x minus h plus 6 in my second last line. And if h is 0, I've got negative 2x plus 6. That is my gradient function. Any questions on that? My last little minute here is just some notation things. I've got an example 4, but we'll do example 4 on Friday. The gradient function is sometimes called the derivative, and the verb is you might be asked to differentiate, or you might be asked to derive. They're the two notations, okay? Or the two pieces of language. So you find the derivative by deriving or differentiating. It can be written as, if you've got the function in terms of y equals f of x, y equals x squared or something, it can be written as y dash. That's pretty common. It is the lazy way, and it's got a couple of problems associated with it with a couple of question types, which I'll explain. It could also be written as f dash of x, which has got the same problems as y dash. And then it can be written as dy dx. Now these two have actually come, historically they come from different places. So there were two people that invented calculus. It could be a mini-series on Netflix, I reckon. But this is Isaac Newton who did this, and this is Leibniz from Germany. This is the 17th century or 18th century, sorry, and they were obviously separated geographically. They didn't have Facebook or anything. So this all happened in a 20-year period that they developed the idea of finding gradients using this method. Similar process, different notations. Turned out that Isaac Newton was also the president of the Mathematical Society of England, and so then he just came out and said that he did it first. But now, historically looking back, they both pretty much did it at the same time. And he sort of refused to publish Leibniz papers. Very dramatical, could be on Netflix. So y dash or f dash of x or dy dx. Now the dy dx is really interesting. Why would we say dy dx? And in purple I've got my reason why here. X plus h is a small change in x. Sometimes h, and you might see this notation, sometimes it's not h, sometimes it's delta x. Delta x can also is another way of saying a small change in x. So you might see x plus delta x. And then the gradient is considered to be the limit as h goes to 0 of a small change in y divided by a small change in x. Delta y over delta x, which then turns into dy dx. That's where that comes from. So you might see that as well, and it's magic. It's not really magic, it's good. Magic being a term I'm using there for something amazing and brilliant. And you might also see variations on that notation. So v dash is pretty common because v can be velocity, v dash is acceleration. You'll see that in our kinematics unit. F dash of r is also common. If you had a function, commonly maybe a volume function, a function of radius is volume or something like that, you might get f dash of r. Dx dt is pretty common. That would be a velocity where t is time. So it doesn't have to be y and x. It could be x and t, it could be r, it could be whatever. But we will be working mostly with dy dx for now. For now, you can use y dash, f dash of x, or dy dx, whichever notation you want, but you'll see all three of them in your textbook. Any questions?